Dear students, welcome back. And today we are going to look into the wave function and its physical property. So far we have seen that when a material particle is moving, it is creating a wave, and that is called the matter wave. So it's a different type of the wave. It is a different from the radiation wave, and therefore we require to represent in a form which can be mathematically will explain, and we can find out its significance, right? So this is what we are going to look into in today's class. So we are taking the wave function and its physical properties. So we know that if you have to represent, let us suppose a electrical vector, right? How the electrical field is going to vary in case of the electromagnetic waves. So you have the electric vector and magnetic vector. So what you have seen in your chapter of electromagnetic wave equation, that this is your coordinate, and along this your electrical vector is going to vary. So this is going to constitute the one component of your electromagnetic waves. Similarly, your magnetic vector is going to vary perpendicular to both your electric vector. So it is going to somehow going to vary like this. So this is how the magnetic field is going to vary. So what I am saying, this is your electric vector, and this is your magnetic vector. So here electric vector and magnetic vector are varying, and with this you are creating a wave, right? Similarly, if you take the sound wave, in case of the sound wave, what is happening? You have the pressure, right? You have the rarefication and the compression of the atmospheric air. So with that pressure, your sound wave is moving. So for anything to represent any wave, we require something which is going to vary. What is that thing that is going to move in case of your matter wave? This is what we are going to look into. So what we are saying, as we know that to write the equation of any wave, some variable is required, right? So what is the variable in case of electromagnetic wave? We have the electric vector and magnetic vector are the two variables which is required to represent your electromagnetic waves. For example, height of the water surface varies vertically in water waves. So if you are taking the water waves, so what is variable? Height of the water, which is ripples, which is going to vary up and down. The pressure of the gas periodically in the sound waves. So you are getting the rarefication and compression, and because of that your sound wave is moving. And electric and magnetic field varies periodically in the light wave. So light wave is nothing, so electromagnetic wave. And in case of the electromagnetic wave, both your electric vector and magnetic vector is varying, right, perpendicular to each other, and it is going to constitute the light wave. But what about the matter wave? In case of the matter wave, the quantity which varies periodically is called wave function, and this is represented by psi, right? So in case of the matter wave, the quantity which is going to vary periodically is your wave function psi. And what is the wave function psi? This is what we are going to look into first. Thus, the wave function psi of a quantum mechanical physical system is a mathematical function which gives all relevant information about the state of the system at position r and instant time. So this is your definition of your wave function. So what is the wave function psi? Wave function psi of a quantum mechanical physical system. So naturally here we are dealing with the quantum mechanics. So we are saying the quantum mechanical physics system is a mathematical function which gives all the relevant information about the state of the system at position r and instant t. So just like your electrical, in case of the light wave, your electrical vector is giving you all the information. Similarly, the magnetic vector is giving you all the informations about any position at any time, how it is moving, what is the velocity, all those things you can find out. Similarly, here the wave function is telling us in the quantum mechanics the entire information about the wave. That is your matter wave. The quantum mechanics that result of the of an operation of an observation of the physical system can be known only if the wave function of the system is known. So naturally, all those properties we can only observe, or we can only visualize once we understand what is the wave function psi. According to uncertainty principle, the result obtained in the quantum mechanics are always in terms of the probability and not in terms of the specific number. So we have already seen that is how the wave function has been created. That also we have seen that a matter particle is moving, then matter particle is going to create a wave packet. Matter particle is going to create the wave packet, and this wave packet is moving, and particle is somewhere within this wave packet, right? But where within this wave packet, exact position is not known. So what we are saying here, we are going to find out its position only in terms of the probability, and this is what the last sentence I have written here. According to uncertainty principle, the result obtained in the quantum mechanics are always in terms of the probability and in terms of the specific numbers, and not in terms of the specific number. So what you can say, wherever the magnitude or the amplitude is maximum, at that position you can say the probability is maximum, and wherever the amplitude is minimum, there the probability of finding the particle is minimum. All right, let's proceed further. According to Max Born, the probability p dV in a small volume element dV at point r and time t can be given as. So how we can measure that probability? So p dV is directly proportional to psi and psi conjugate into dV. So I am just going to come in. So what is this psi and psi conjugate in the next slide? So what we can say, this is directly proportional to probability is directly proportional to psi and psi conjugates, right? So this is what we can say, psi into psi conjugate is equal to your psi whole square. So how we are going to find out the probability that particle is within this wave packet, or naturally in terms of the probability. So what is the probability? We are finding where is the particle. So what we can say, the particle is within somewhere within this wave packet, but where exactly, that is not known to you. So how to find out the probability? So this is what the Max Born probability concept says. Let us suppose its volume is dV. So its volume is dV, and we are going to represent this wave function by a quantity called psi, because here this wave function itself is variable. So we are going to represent this by psi. Then what we can say, p dV is directly proportional to the psi, that is probability of finding the particle within this volume dV is directly proportional to psi and psi conjugate, right? So what we have done here also you have the dV, here also you have the dV I have taken out from both the side. So what we can say, probability is directly proportional to product of psi and its conjugate, that is p is directly proportional to psi whole square. Now let's try to understand what is your psi and what is your psi conjugate. Psi, you have understood, is a function which is associated with the variables. So what is the variable over here? The wave packet is your variable. So we have associated the function psi with the wave packet. So the way the wave packet is going to move, the matter wave is going to constitute. So all the property of the matter wave is going to determine by using the wave function psi. Like in case of your electromagnetic waves, with the movement of your electric vector and magnetic vector. So how your electric vector and magnetic vector is going to move, what is the ratio between the electric vector and magnetic vector, right? So based on all those things, you can find out all the property about your electromagnetic waves. Similarly, here the wave packet is going to move. So if you are going to associate a function to the wave packet, right, then if you are going to measure that function, then that function is going to give us all the property about that wave packet. So let us try to understand it in little more detail, right? So what we are saying, so what is the psi? Psi is a wave function which you have associated, and psi star is called psi conjugate, right? So a star of that is called your conjugate, that I have already explained you. So probability is product of psi and psi conjugate, which we are calling this mod of psi whole square. So the probability of locating a particle must be large if the amplitude of the wave is large. So this is what I explained you with the diagram there. If the amplitude is large, and probability must be 0, right? Or you can say minimum if the amplitude associated with the wave is 0. So if it is exactly 0, then what we can say, their probability is 0, right? Because the amplitude itself is 0. Thus, psi is also referred as the probability amplitude. So psi, we can also say psi is a probability amplitude. So again, to take it here, if you are going to vary this, so this is how your psi is going to vary. This is your one wave packet. Then again we have the second wave packet like this. So this wave packet is going to move right in this way. So the wave function psi is associated with this. Now here we can say its amplitude is 0. So naturally we can say probability of finding the particle over here is 0. And again here what we are finding here is a maximum. So what we can say, the probability of finding the particle is maximum over here, and here again it is your 0. So here we can say it is again 0. The probability of finding the particle is also 0. So the probability is going to vary from 0 to a maximum particular value. But if we are going to consider this entire wave packet, right, entire of this, so the particle is definitely somewhere within this wave packet, and that will be your 100%. So psi is also referred as the probability amplitude, right? All right, so let's move further. Since the wave function psi is a complex and it has no physical meaning. Now wave function psi that we have taken is a complex form. It's not a classical form, it's a complex form, and therefore it has no physical meaning. So what is the complex form? If we say if any function is, let us suppose psi, then psi equal to a plus ib, then that's your complex form, where a is your real and b is your complex, right? So what we are saying, since the wave function psi is a complex, it has no physical meaning. However, the product of these two, that is psi and psi conjugate, is always a real, non-negative, as shown here. Let us suppose we are saying the psi is equal to a plus ib, then naturally its conjugate will be a minus ib. If I am going to take the product of the psi and psi conjugate, then what we can say, a plus ib into a minus ib, and this is your a plus b into a minus b, a square plus b square, I square is equal to minus 1. So this is what we are going to get over here. So therefore a square plus b square. So a square plus b square is a non-negative number and is always a real number. So what we are saying, if you are going to multiply the psi with its conjugate, then always we are going to get a real number, and therefore the wave function should be, probability density should be taken as the product of psi and its conjugate. Then only we can say where is the particle, where a and b are the real function. So what we can say, since mod of psi is interpreted as the probability density, right? Probability density, psi must have some property. Okay, so I am coming in this. So what I am saying, so here if you are taking the psi into psi conjugate, so then we can say this is your mod of psi whole square. So mod of psi whole square is equal to your how much? Mod of psi whole square is equal to a square plus b square. So this mod of psi whole square is also called your probability density, right? If it is a probability density, so it must have a certain properties, and let us look into what can be those properties, so that it is not going to violate any fundamental principle. All right, so let us see some of its meaningful properties of the wave function psi. First, psi must be continuous and single valued everywhere. Now it should be continuous and single valued everywhere. That is, does mean at any instant it should not have two values in the space, right? Naturally. So why we are saying it cannot have the two value? Let us suppose if I am going to find out about the property of the psi at any instant t and position r. So this is your position. Let us suppose this position is your r, and this is at any instant t. So here we have only one probability. So this is one particular probability. So at one point you cannot have the two probability. So it cannot be. You cannot have the multiple value. So psi must be continuous and it must be single valued everywhere, right? So anywhere in the packet, if you are going to look into, is must have only one value, and that must be the property of your wave function. So if wave function has more than one value at any point in the space, it would give more than one probability of finding the particle at that point in the space, and naturally that is not possible. So second one, the first derivative. So let us suppose we have taken the wave function as this psi. So you take the first derivative along the x direction, y direction and z direction, then you are getting in the space, or the wave function is moving in the space. So first derivative along the x direction, y direction, z direction must be continuous. Firstly, the psi itself should be continuous and single valued, and its first derivative should also be continuous, and it also must be single valued everywhere. So you cannot have two value of its first derivative as well. The third, we are saying psi must be normalizable. Normalizable does mean the probability density. This the more detail we'll discuss later in the next slide. This, it does mean the probability density. What is the probability density? Mod of psi whole square, mod of psi whole square, and in a particular volume, let us suppose that volume we are saying dV, and that wave packet is spread from, let us suppose, minus infinity to plus infinity. As you know, it's not a fixed size. You can have the different size. It can be between x1 to x2, it can be between 0 to x, it can be minus x to plus x. So it can be, it can have the multiple range. So what will be the maximum range? Minus infinity to plus infinity. So let us suppose we are saying this is your wave function, right? So it can spread from minus infinity to plus infinity. So if I'm taking the coordinate over here, so this side I'm saying this is minus infinity, right? And this side I'm saying is a plus infinity. And this volume I'm going to represent by dV. So minus infinity to plus infinity within this wave packet dV is equal to 1. So if the probability value is coming out equal to 1, so the probability in this wave packet from minus infinity to plus infinity, and that probability is coming out to be equal to 1, that is called normalization. So psi must be normalizable. This is the meaning of this, right? All right, then let's come to the next one. Psi must be finite everywhere. So at any point, naturally it cannot be should not be infinite. And the next one, mod of psi whole square dV cannot be equal to 0, it cannot be infinity, and it cannot be negative, right? Because if it is going to be 0, it does mean particle is not there at all. Particle is not there at all. Naturally it cannot be infinity, and it cannot be negative. It is, if it is within the wave packet. Therefore only a possibility that is left is that its value must be finite quantity. That is, mod of psi whole square dV must be a finite number, right? 1 is the maximum probability. It can be 0.5, 0.3. 0.3 does mean 30%. 0.5 means 50%. So it must be a finite number, right? The probability cannot be negative. It cannot be infinity, right? So that is the meaning of this. Mod of psi whole square dV should not be equal to 0 or infinity and negative. This value is not possible, right? So these are properties of your wave function. So if all this property is going to be followed, then what we can say, this is your function that you can use for your mathematical calculation, right? Now let us see a bit about the normalization of the function, about which I have just explained you. So we know that the probability of finding a particle in a volume dV, so just I have explained you, this is your probability density, PdV is your psi into psi conjugate dV, and we also call mod of psi whole square dV, right? The probability that the particle will be somewhere in the space available must be equal to 1 is called the normalization. So within this, mod of psi whole square dV is coming to be equal to 1, that is called your normalization. So what I am saying, minus infinity to plus infinity, PdV, that is your probability density, is equal to, so PdV is equal to how much? Mod of psi whole square, right? Or you can write psi into psi conjugate dV, whatever you want to write, you can write. So what we can say, integral minus infinity to plus infinity psi into psi conjugate into dV, or mod of psi whole square dV must be equal to 1, and that is called the condition of normalization. So where we use the condition of normalization, if we have to find out the probability of finding the particle in a wave function, then we are going to use the condition of the normalization. That we'll see while we will be writing down the wave equation, and we will be taking the applications of those waves. The wave function which satisfy these conditions are called the normalized wave functions, and the condition is called normalization condition, right? So all those wave which is going to follow this condition is called your normalized wave. That is probability, the mod of psi whole square within your limit minus infinity to plus infinity is equal to 1 is called your normalized wave, and this condition is called normalization condition. Now some of the wave may not be normalized, so you can multiply that wave with a certain constant, or you can divide so that it can become a normalizable wave. So unnormalized wave is not possible, right? So we can convert this into a normalized wave, right? The much detail of that I am not going over here. And finally I'm coming to your probability. Now what you have to do is you have to locate the particle in terms of the probability. So let us suppose this is your extended from minus infinity to plus infinity. So it does mean it is somewhere within this, between minus infinity to plus infinity, particle is somewhere there. But now you have to find out what is the probability of finding the particle between any two limits. Let us suppose those limits are x1 and this your x1 and another is your x2. So what is the probability of finding the particle, right, within a given limit? And that is your call your the probability. So probability between the limits x1 and x2 is given by, so p x1 x2, that is the probability of finding the particle between the limits x1 and x2 is mod of psi whole square dx and x1 x2. So you go ahead and integrate this, you'll be getting what is the probability of finding the particle over here, provided the detail about your psi is known to you. What is the psi? That is known to you, whether psi is a sine wave, cosine wave, or how it is a variable, what is a propagation constant. All those things is known to you. You can integrate that, and by integrating this you can substitute the value of the limit and you can find out what is the probability of the finding the particle within that two limits. So those applications will be saying both theoretically and in the numerical problem. So from next class we are going to start the writing down the wave equation based on all these concepts. Thank you very much.